In the previous video, I have explained about a liquid level control system in which I have explained all the variables which are associated with the closed loop control system. I also explained how the variables are changing with respect to the time and how to denote each variable also, and what is the definition, what is the difference between the initial value and the deviation. All these things were explained very well in the previous video. So I advise all the students who are going to watch this particular video, please go and watch the previous video. Otherwise, it will be difficult to understand the variables which are associated with the control system. Now, if you look at this block diagram, you can clearly understand set point is given as IS cap of t, which is nothing but 4 into u of t. I told you what is the meaning of IS cap of t in the previous video. So as I said, please go and watch the previous video and then continue so that it will become very easy for you to understand the next half an hour section. Now, IS cap of t is equal to 4 into u of t. This means that the deviation in the set point is a sudden deviation, that is of 4 units. 4 into u of t means it is actually 4 milliampere current, right? So now controller, we denoted with some function f. It means that the function, it might be proportionality in the case of proportional controller. Now the controller takes the error cap, E cap of t, as an input. This E cap of t is nothing but the deviation in the error from the initial steady state point. Now this error will be taken as an input and it will going to generate some current or the deviation in the controller current. So IC cap of t. I have explained very clearly in the previous video what is the difference between IC of t and IC cap of t. So please go and watch that. Now when the actuator comes into the picture, it converts the current into suitable fluid flow rate, because actuator converts the electrical input into mechanical output. Now for the easy understanding, intentionally I have taken the gain of the actuator is equal to 1. And one more thing I would like to say, all the components whatever we are using here, I presumed that every component is working linearly. Now this actuator changes the fluid flow rate which is entering into the liquid level, as I said in the previous example. Naturally, for different fluid flow rates, we will be able to see different water levels in the tank. So obviously the water level in the tank or the deviation in the water level from the steady state point, that will be fully under the control of this input fluid flow rate deviation, right? Now the mathematical equation which governs this first order liquid process is dHm of t by dt plus hm cap of t is equal to qin of t cap. So this equation clearly says that whatever the liquid level tank we have discussed in the previous video, that is a first order system. Now the liquid level in the tank is going to be monitored by the transmitter, and the transmitter will going to generate the current. Okay, so as I said, our final aim is we need to make this E cap of t is equal to 0. This hm cap of t should be equals to 0.5 meter at steady state. Then only the total water level in the tank will going to become 1 meter, because we clearly know that hm cap of t is not the water level. hm of t is going to be the water level. hm of t is going to be the water level, right? So the relation between hm of t and hm cap of t is equal to hm cap of t plus 0.5 meter. These things you need to know. Clear? Because if you bring this value to 0.5 meter, then this value plus this value together, it will become 1 meter. So the ultimate aim for the controller here is try to make this hm cap of t equals to 0.5 meter. As I said, this water level will be measured by the transmitter, and then the transmitter will going to generate the current. So now the error E cap of t is nothing but the deviation in the set point minus the deviation in the transmitter current, that is IM cap of t. Now let us look at slowly one by one. So when you see the set point current, that is IS of t is equal to, as I said, the deviation plus initial set point, that is initial steady state point, and IM of t is actually nothing but the transmitter current with respect to time is equal to the deviation in the meter current, that is IM cap of t, plus initial value of the meter current, that is IM of 0. Now as we already know, initially at time t equals to 0, that means before we change the set point, before we change the set point, the value of set point current and the transmitter current both were equals to 8 milliampere. In fact, this is the initial steady state point before we change the set point, right? So now, if we calculate the error here, so how to calculate the error here? Naturally, the error E cap of t can be given as, or E of t can be given as IS of t, the set point here, minus IM of t, that is transmitter current. But if you look at here, IS of t is this value and IM of t is going to be this value. Now when you take the difference between these two, this and this both will going to get cancelled, and you will going to get happily IS cap of t minus IM cap of t, and this will be denoted as E cap of t. That is nothing but the error between the deviation of the set point and the deviation of the transmitter output from the initial values. Now, if you look at carefully, this IS cap of t, as we know very well that this IS cap of t is equal to 4 into U of t, that is nothing but step input. We can easily write E of t is equal to 4 into U of t minus IM cap of t. Now, one more thing I would like to address here. If you look at the deviation in the flow rate, Qi of t can be given as K dash into IC of t cap, which is coming out of the control valve. Naturally depends on the current given to the control valve. So that I have written like Qi of t, Qi cap of t is equal to K dash into IC cap of t. But K dash is equal to 1. That's why I used 1 here. So please make a note about this one. Now let us look at the other story here. So we have seen here the error with respect to time. The error with respect to currents. Error in terms of HS and HM. What is HS? The required water level. What is HM? The measured value of the water inside the tank. Right? So now E of t can be written as error at any particular time, that is equals to required water level minus measured water level. This is called set point and this is called process variable. Now if you still go one step ahead, this can be removed, HS of t plus H of 0 minus HM of t plus HM of 0, because I told you that a variable with respect to time in our example can be written as deviation plus initial steady state value. I sincerely advise, before watching this video, please go and watch the previous video so that it will become very clear to you. Minus HM cap of t plus HM of 0. Now as we know that before we change the set point to 1 meter, initial value of the water level was at steady state, that is HS of 0 is equal to HM of 0 is equal to 0.5. Now if you substitute these values here, this will going to become like E cap of t is equal to HS cap of t minus HM cap of t. Clear? And we also studied in the previous video that I also explained in the previous video that the relation between the deviation of the water level and the deviation of the current is equal to H of t cap equals to 1 by 8 I cap of t. Suppose if I say how the deviation of the water level in the tank and measured current associated, then this will going to become like HM of t cap equals to 1 by 8 IM cap of. That's all. This is the relation between water level and current. Okay. Suppose if I ask like how HS of t cap and IS of t cap related, then instead of M you try to use S, then it will going to be clear to you. Clear? So now let us come back to the discussion. So as I said, E cap of t is nothing but the deviation in the error. That can be either written like HS cap of t minus HM cap of t, or else you can write down like IS cap of t minus IM cap of t. As the relation between water level and the current both are linearly associated. There is no difference even if you write the error in terms of water level or if you write error in terms of current, because the percentage of error remains same if these two variables are associated linearly. Right? Now let's go deeply into the topic. As we know, error E of t also can be written as E cap of t plus E of 0, but initially there is no error. Right? Before we change the set point at 9 o'clock, there is no error. That's why I have mentioned like E of 0 is equal to 0. If you take E of 0 is equal to 0, then absolutely E of t can be written as E cap of t. This means that hereafter there is no difference even if we write like E of t or even if you write like E cap of t, because the initial error is 0. Right? Now look at this diagram. If you look at this diagram, we can quickly observe these things. dHm cap of t by dt plus hm cap of t is equal to q in cap of t. That differential equation if you take and if you write, you will going to get like this. But how can we change the q in cap of t? Q in cap of t here is nothing but 1 into IC cap of t. That is what exactly I have written here. But this IC of t is actually nothing but some function of this error, that is deviation in error. As I said, there is no difference even if you write like E cap of t or E of t. But for understanding purpose, it is better to write like E cap of t only. Okay. So now if we still go, suppose if you use proportional controller, let me take here proportional controller. If I use proportional controller means we will write like P controller. I request all of you, please have a look on this one. That is P controller means proportional controller. इसका मतलब क्या है? What does it mean? It means that proportional controller means whatever the function we have used here, right, mathematically, that is nothing but a simple constant. So we have to write this f is nothing but kp, nothing else. That means this value now here it is going to be a simple kp, that is a constant gain. So IC cap of t is equal to kp into E cap of t. This is what I would like to say. Now if you use like this, then how the things will going to change? Now anyway we are actually looking into the water level. That means we are operating the differential equation in terms of h. So dhm cap of t by dt plus hm cap of t equals to kp into, that is function is kp now, into E cap of t in terms of height. Correct? Because left side we have meters. Okay, right side it is your responsibility to have a meter, obviously, right? So hs cap of t minus hm cap of t, that is what I have written. Now when you convert this equation into current, because ultimately it will be required to convert the values into current, because the transmitter only generates the current to the control room, right? So now hm cap of t can be written as 1 by 8 into Im cap of t. How we have written like this from here? hm cap of t is equal to 1 by 8 into Im cap of t plus 1 by 8 into Im cap of t. This one is going to be this one, equals to kp into 1 by 8 into Is cap of t minus 1 by 8 into Im cap of t, right? So now after substituting all these things, if you multiply with the 8 on both sides, this 8 here, all these 8s we are going to get cancelled. Then naturally the differential equation looks like this, that is d Im cap of t by dt plus 1 plus kp into Im cap of t is equal to kp into Is. Now if you look at this equation, it looks like a differential equation of first order, right? So now if you rewrite this slowly, d Im cap of t by dt plus 1 plus kp into Im cap of t is equal to kp into this Is of t can be written as 4 into u of t, but for all t greater than or equal to 0, that means after 9 o'clock in the process, Is cap of t will be equal to 4. That I have written exactly here. Now after this much of effort, we got a differential equation, and if you solve this differential equation, we will be able to get how the current of the transmitter will going to vary. That is, the deviation of the current will going to change, Im cap of t. Now for understanding purpose, let me take this equation once again here, that is from here. So if you solve this differential equation by using any of the linear differential equation methods, then you will be able to get the value of Im cap of t to e power integral PDS, that is 1 plus kp into dt equals to integration of q, that is 4 kp into e power integral of 1 plus kp into dt plus c. So this is actually nothing but integration factor. This is very casual way of finding the solution of differential equation, right? So from here, if you slowly find the value of our equation of Im of t, it comes like this. Im cap of t is equal to 4 kp by 1 plus kp plus c into e power 1 plus kp into t, of course minus here, right? We know that at t is equal to 0, that means at starting that Im cap of 0, that is equal to 0 milliampere, right? Now if you substitute this here, then the value of C will be equals to minus 4 kp by 1 plus kp. Okay? So with this much of effort, we were able to get the value of C. Now if you take this value of C here and if you substitute, then you will going to get how the meter current is changing or transmitter current is changing with respect to time. Yes. After finding the value of C, we can write down the current, that is Im cap of T is equals to 4 kp by 1 plus kp into 1 minus e power 1 minus kp plus T. Now, the actual current of the transmitter can be written as Im of T is equal to, we know that the deviation in the meter current, that is Im cap of T, plus the initial current of this one, that is Im of 0, right? So if you slowly understand this, the value of Im of T would be something like this, that is Im cap of T is this, and we know this value is actually 8 milliampere, that we already discussed earlier also and in previous video also. Now if you substitute 8 here all the way, this looks like this, that is 4 kp by 1 plus kp whole into 1 minus e power minus 1 plus kp into t whole plus 8 milliampere. This is the way how the transmitter current varies with respect to time. In fact, it varies from the initial value like this. This is Im of T. Now, what will be the corresponding value of water level with respect to time? We already discussed many times up to now that Hm of T can be given as 1 by 8 into Im of T minus 4 milliampere, right? Now, if you substitute this, the value of Hm of T or the variable of water level with respect to time, it will going to come like 0.5 times of kp by 1 plus kp 4 by 8.5. So it will going to become like this, 1 minus e power minus 1 plus kp into t whole plus 0.5 meter. Clear? This should be in meters and this should be in milliampere altogether. This is going to be in milliampere and this should be actually in meter. Clear? So after all these things, we have found the equation for transmitter current with respect to time and water level with respect to time. Now, having observed this, we can also find from here the error in terms of current. Anyway, error can be found in terms of current as well as in terms of meters because the percentage will remain same, right? So from here, we can easily say the error E of T can be written as, we can take caps or else we can take in normal way because initial value is same, that is IS of T minus Im of T, right? So this is going to be equal to, all the way we can write down, if you substitute all these things, then you will be getting 4 by, give me 1 minute time, so it will going to become like 4 by 1 plus kp whole into 1 plus kp by 1 plus kp whole into e power minus 1 plus kp into t. This is actually the way how the error will going to change with respect to time. And out of all these things, the interesting fact is, if you look at the current, how the current will going to change, because this can be even said as, you can say this also, right? This E cap of T is equal to IS cap of T and cap of T. Now, after this much of effort, if you try to investigate how the controller current changes here is, let me write down here, otherwise controller current, that is IC of t is equals to IC cap of t plus initial current of the controller, that is IC of 0, right? So this could be written as IC cap of t can be written as Kp into E cap of t, E cap of t plus IC of 0. So this can be equals to, because we have E cap of t that is equal to this, where IS cap of t is nothing but 4, and IM cap of t can be written from here. This you can take here, and if you subtract, we will going to get this. Now if you use this equation here, it will going to become all the way 4 into Kp by 1 plus Kp whole into 1 plus Kp by 1 plus Kp into e power minus of 1 plus Kp into t, plus still we have initial controller current, that is nothing but what? How much is the controller current initially? IC of 0. IC of 0, we know that initially it is actually generating 12 milliampere. Controller bias is 12 milliampere, controller offset, right? So with this, we were able to chase how the water level is changing with respect to time, or the transmitter current is changing with respect to time, and we were able to find how the error is changing with respect to time and how the controller current is changing with respect to time. Because once you understand all these things with respect to time, then it is very easy to understand or draw the graph to get the idea like how the variables are changing. Now let me show here in a simple way, that is time. Let me show how the variables are varying here with respect to time, and let me consider one more variable here, that is a meter current Im of t, right, and then Hm of t, water level, and then error E of t, right, and then we can also see the way how the current is changing with respect to time, that is nothing but IC of t. Now at t is equal to 0 seconds, that means starting. What is Im of 0? Im of 0, we know that at starting, transmitter generating the current of 8 milliampere, because the water level at starting is just only 0.5 meter and it is fixed. At starting it is at steady state, right? And error is going to be at t is equal to 0, right? So if you look at the moment when we apply, exactly the moment when we apply the set point variation exactly greater than 0 instant of time, because the water level will not change suddenly, but error can change. That means I am talking about E of 0 plus, let me say 0 plus here, that is just after 0 second, maybe like 0.0001 second. The error could be equals to 4 milliampere, right? Because we know that this Im cap of t is, Im cap of 0 is equal to 0, but Is cap of 0 is equal to 4, right? So that means let me give a small attention here, that is Is cap of 0 is equal to 4 milliampere in fact, right? But Im cap of 0, how much it will be? That is equal to 0 only, right? Now initially it not deviated the meter current, then 4 minus 0, it will be equal to 4 milliampere. And then what about this IC cap of t? IC cap of t, if you substitute here, you will be understanding that t is equal to 0. So the IC of t is equal to 0 if you substitute, and we need to take the value of Kp to understand this. Let me select the value of Kp is equal to 1. That means proportional gain is equal to 1. If Kp is equal to 1, let us look at what will going to happen for IC of 0. IC of 0, I am damn sure that if you solve all these things, then you will be able to get that as 16 milliampere. Clear? Because it's quite easy. How we can say IC of 0 plus is equal to Kp into error plus initial bias of the controller. Kp into error means Kp is 1 into 4 milliampere plus initial 12 milliamperes of the controller output. Totally it will become 16 milliampere. Now the great thing is, if you just see for some other times 0.1 second and 0.5 seconds, and if you continue like that up to infinite seconds, means steady state. Let us see how the things will going to change now. Now I have already calculated these values. It is your turn. Just try to note down these values. It will be clear to you. At 0.1 second, this value will be of 8.36 milliampere, and this value of 0.545 meter, and this will be of 3.64 milliampere, and this will be kp into error plus 12 milliampere. So how much you are going to get? That is 15.64 milliampere. Right? Now if you look at 0.5 seconds, or else if you are not able to get this, it's very simple. Just take 0.1 second and substitute in this equation IC of 1. Then you will be able to get, after solving this, you will be able to get 15.64 milliampere. It's very easy. Now at 0.5 seconds, the current of the transmitter will be of 9.26 milliampere, and this will be equals to 0.6580 meter, and this is going to be 2.74 milliampere, and this one will be at a 14.74 milliampere. Clear? So at infinite seconds, because infinite is actually called practically steady state. Infinite seconds means if you wait for large amount of time or so much amount of time, then what will going to happen for the transmitter current here? So if you wait for infinite seconds, just substitute infinite here in Im of t. If you substitute infinite here, this will die off, right? Kp you have taken like 1, 4 into 1 by 2, it will be 2, 2 into 1, 2 plus 8. So totally it will going to become 10 milliampere current after a lot of time, right? What about the meter height? So we know that the relation between meter height and the transmitter current the relation between water height and the transmitter current is 1 by 8 into this. Im of t, now we know that is 10 milliampere. 10 minus 4, 6 by 8. So it will come like 0.75 meter. So this is going to be the value what we are going to get, right? Now what about this one? Here it continues, and it will going to become 2 milliampere, and here the controller current will going to come to 40 milliampere. Clear? 14 milliampere. If you substitute t is equal to infinity in this expression altogether. That's all, right? So what I would like to say here is, have you understood the water level in the tank is slowly increasing from initial value. This is initial value of the water inside the tank. Slowly it is getting increased, and finally water level is stopped at 0.75 meter, right? And if you look at, the error is gradually decreasing, but unfortunately we haven't reached the actual or ideal target of the control system. The reason is, even after waiting such a long time, we were not able to get the error is equal to 0. Clear? We still struck at some point 2 milliampere. This is called steady state error. This is actually called steady state error, 2 milliampere, right? And anyway, controller current is slowly decreasing. Why it is decreasing? It's quite easy to understand. When the error is decreasing in the next instant of time, automatically the controller current will going to decrease. Am I right? Of course, because when the error is decreasing, naturally the controller current will going to decrease, because we are using proportional controller, right? Now, how much is the water level we require? 1 meter at steady state. But how much we got? 0.75 meter, right? So we require water level to be equal to 1 meter, but we just got only 0.75 meter. Then what is the error here? 0.25 meter is going to be the error, right? In fact, that is going to be less amount. We need to get 1 meter, but we got only 0.75 meter. So 0.25 meter is the error. So that means here the percentage of steady state error can be given as equals to, percentage of steady state error can be given as equals to amount of error, that is 1 minus 0.75 in meter by 1 meter into 100. That will come down to be equal to 25% error is there even at steady state. Clear? So this is the biggest challenge with the proportional controller. Unfortunately, whatever the gain you may use, or even if you increase the gain, this steady state error cannot be eliminated. This means you will not able to reach to the 1 meter height. I mean, water level will not reach to the 1 meter height. Now, some people think like this. Why can't we change the gain here? Suppose instead of 1, if I say something like instead of 1, if I keep like some other value, probably let me select here 10. If I select 10 as a controller gain here, right, then we will see what happens. So obviously it will be quicker response. We are going to get quicker response. That means whatever the value we got at 0.5 second, now as the gain is increased, this value of the water level will be reached even in very less time. So that means speed of response is increased. This point to be noted. But ultimately at steady state, if you look at, just nothing else. If you want to know how at 0.1 second what are the values, take Kp is equal to 10 here and substitute the value t is equal to 0.1 second. Then we will be able to get what is the Im of t. If you substitute Kp value here, you will be able to get Hm of t. All the relations are there, so it is very easy to understand these things. Now at steady state, let me discuss at steady state. At steady state, if you keep t is equal to infinite and Kp is equal to 10, let's see what will going to happen. If you keep Kp is equal to 10, it will become 40 by 1 plus 10, 40 by 11, and substitute 10 here. All the way, if you do it properly, then you will be able to get this value is equal to 11.6 milliampere steady state value. If it is 11.6 milliampere, and if you use that value here, then you are going to get Hm of infinity, which is actually nothing but 0.95 meter. Clear? And this error obviously is very less now. 0.95 meter means the error will be equals to 0.4 milliampere approximately, and this is going to be 15.6 milliampere. Clear? So these are the way, this is the things which will going to happen when we have Kp is equal to 10. The great thing about this is, see, as I said, this is quite simple here. So 0.4 you will multiply with the 10, we will be having almost 10 into 0.4, 4 plus 12 milliampere. This will come down to be nearly equal to 16. Actually, this is slightly less than that one because I have to round off values, so that's why it is coming like this. Right. Now, have you understood one thing? At steady state, now the water level is 0.95 meter. But how much we require? 1 meter we require. So that means percentage of steady state error. Now it can be look like this. That is 1 minus 0.95 meter by 1 meter into 100. So it will come down to be equal to 5%. So that means in this particular case, when we use Kp is equals to 1, percentage of steady state error, it was equal to how much? 25%. But when we use Kp is equal to 10, percentage of steady state error, it is coming to be equal to 5%. Clear? So this means that if the gain is increased, there is a chance that the steady state error will going to decrease. At the same time, the speed of the response is going to be increased. But when I ask this question, most of the students says that the ideal value of Kp should be equal to infinite, because we know that when we increase the value of Kp, we are getting, interestingly, the desired values. That means steady state error is decreasing and the speed of response is increasing. Right? So let me conclude the topic here. That is, if Kp is increased, then it leads to two effects. One is steady state error is decreasing. Second one is speed of response is increasing. That means we will be able to reach a set point very quickly according to the meaning of this. Speed of response increases. Clear? So obviously these two are the fundamental requirements of any control system or any controller. So we are getting this one. But the problem here is, have you noticed this one here? The current of the controller, if you look at carefully, look at this one here. Then you will be able to understand easily. That is, so if you look at the controller there, IC of T should be, that is controller output should be between 4 milliampere to 20 milliampere. This is the standard range of the controller current. Clear? So but unfortunately, if you look at IC of T, we know that is IC cap of T plus initial current 12 milliampere whole should be less than 20 milliampere. Clear? So that means IC of T maximum for the extreme limit, IC of T should not be more than 8 milliampere. This is the fundamental line you should remember. Clear? So that means there is some constraint with the error band actually. Okay? So or else you can look at the same thing in a different way. So IC of T, how we know that the IC of T here, this IC of T can be always written as, that is the controller gain Kp into error E of T. Correct? So this value should not be more than 20 milliampere and it should not be less than 4 milliampere. Now have we looked at this one? If you increase the value of Kp here, right? So then naturally, even for the smaller, if you increase the value of Kp, right? So then for the smaller values of error, this product may be, there is a possibility that product may be more than 20 milliampere. So that means there is a threshold here, you should not cross 20 milliampere. That means we cannot increase the value of Kp further to some extent. Okay, that means there is always a limitation on the Kp. Okay, so how much Kp we can keep? That depends on the error band. That means limitation of the error band. What might be the error band you are able to use here? If I say error band this much, if I say the error value should be this much maximum, then from there we will be able to find the Kp value. If I say somebody is saying like error E of T can be maximum of 4 milliampere, then Kp into 4 milliampere should be less than 20. Then Kp can be less than 5. Clear? So that is the way this error band is going to decide or keep the constraint on the controller gain Kp. Clear? So the error band for which controller output reaches from minimum to maximum or maximum to minimum, that means from one extreme to another extreme, that particular error band is actually called as proportional band. So that means indirectly this Kp into this error band, Kp into error band can be written as proportional band. I already told you proportional band means the range of error for which controller takes the extreme action from one extreme point to another extreme point. Okay, Kp into Pv, that should be actually the 100%. So then Kp or Pb, proportional band or error band, can be given as allowable error band. That is the meaning of allowable error band, 100 by Kp. So that means we cannot increase the value of Kp. The reason is if you keep on increase the value of Kp, what happens now? If you keep on increase the value of Kp, then the proportional band will going to decrease. This means that the limitation with the proportional controller is if Kp is increased after some limit, after some extent, there might be a chance that proportional band will going to decrease. If the proportional band is decreasing, then slowly it looks like it converts like on-off controller. Clear? So it's quite simple. That means proportional controller with high gain. That means if you increase the value, keep on too much Kp, then it turns to be on-off controller. On-off controller. So this means that in this particular problem, even for as the Kp is very high, let me take like this. As the Kp is very high, this is high. If the error is a very small positive quantity, this product will be more than 20 milliampere. That is, practically it will be equal to 20 milliampere, and the valve will be in extreme position, either fully open or fully closed. And suppose if the error quantity is negative, let me write down here. Otherwise, that is, if E of t is a greater than 0, then Kp into E of t, because Kp is very high value now, this Kp into E of t is going to reach to the saturation, that is 20 milliampere, because above 20 milliampere is not possible. Okay, so when it is 20 milliampere, then valve will be at extreme position. Valve will be extreme position. Extreme position means either it is going to be fully open or fully closed. Okay, suppose if E of t is less than 0, if the error is slightly less than 0, right? So then Kp into E of t, high value into negative error, will be to this extent, that is less than 4 milliampere, right? But it's not possible, so it will go into saturate at the lowest limit, that is 4 milliampere. In this case, valve will be in another extreme position. Valve will be in other extreme position. Extreme position, right? So what does it mean? It means that if it is fully closed here, fully open here, then it will be fully closed here. So that is, for minute errors, extreme action will be taken in case of on-off controller. So with this, I have completed both proportional controller as well as on-off controller. Now let me conclude the things. Then, if we increase the gain of the proportional controller, then the steady state error will going to reduce, which is the desired parameter or desired situation, and speed of response will going to increase. These two are the advantages if you increase the gain of the proportional controller. But if you increase the proportional gain, then the proportional band will going to decrease. And if the proportional band is still decreasing, then there is a chance that the proportional controller will turn and act like an on-off controller. Clear? Now to understand about integral controller and derivative controller in detail, just follow up the next 2 videos which are present in the channel. Hope you enjoyed the video. Thanks for watching, and if you want to find more of this kind of questions, connect to my channel. Namaste.